Chapter 4, Vector Spaces, Section 4.1, Vector Spaces and Subspaces. So in this chapter, in this section, we will define what is a vector space and what are subspaces of the vector space. Now you have already learned about subspaces in chapter 2. There we were talking about subspaces of Rn, and what are the vectors look like in Rn. We define them like this, like a1, a2 up to an. This will be a kind of a vector in Rn. So these are the vectors, but the vectors will not always be of this shape. There are many other objects which satisfy these conditions, and so they can be also be designated as vectors. I will talk about those in a few minutes. Right now we are looking at the definition of a vector space. We say let V be a set on which two operations, vector addition and scalar multiplication. So some kind of addition. It doesn't have to be our usual one, like 2 plus 3 is equal to 5. Your addition might say 2 plus 3 is equal to 9, something. So we will see examples and you will understand better. So we need two operations, addition and scalar multiplication. So if those two are defined, what does that mean? Means if you add two vectors or two objects in the set, you must get the answer or the resultant inside the set. And then if you take an object from the set or a vector from that set and you multiply it with any constant or any real number, the resultant must be in the set. Then the set will be called, and on top of that, so those two operations should be held, and then on top of that, the vectors in that set must satisfy these 10 axioms or 10 rules. If the set does that, then it will be a vector space. Now you will see problems of the form that you have that such and such set is defined. Now to show that this is a vector space, or it could be that okay, given this set, show that or determine whether it is a vector space or not. So what do? If we have to show that a certain set defined with an addition and scalar multiplication is a vector space, we have to show all these three axioms, that all these 10 axioms are being satisfied. And if we have to determine whether a given set is a vector space or not, we have to check one by one each axiom. It could be that the first two are being satisfied, third is not satisfied, so we will stop there and say that the set is not a vector space. If 5 of them are being satisfied, the 6th is not being satisfied, then we say again we will stop there. And so if 9 of them are being satisfied and 10th is not being satisfied, we have to show all that and then show that the 10th is not. But not always we have to do that. We don't have to do always all of these. If you can see, if you can assess which axiom will fail, you can directly go to that. So at least one axiom should fail, then it will not be a vector space. Now we usually use the addition symbol for the addition of in the vector space, and the dot uh, for multiplication, scalar multiplication for the in the vector space. But these are used when we are talking about the standard addition and standard scalar multiplication. I will show you some examples. What do we mean by standard operations? And if they are not standard operations, if the addition or the scalar multiplication is defined in another way, then we will use the symbol, this, the plus sign inside a circle for addition and the dot inside a circle for the multiplication. So we will circle those addition and dot symbol, addition and multiplication symbols, just to remember that we are not using the standard addition and multiplication. Now there are some properties of scalar multiplication. So along with those 10 axioms, the vectors also satisfy these properties. First one, that 0 is a scalar. 0 times u, a vector u, will be a vector. Which vector? It will be the 0 vector. Remember, if you have a vector and you a1, a2, and you multiply by k, so you get a ka1, ka2. So you get a vector which is still the similar type of vector. So size is the same. So it should be in the set from where this vector is coming. So, but when you multiply by 0, 0 is scalar, so we get a new vector which is the 0 vector. Now, if number 2 here, saying c times 0 vector is equal to 0 vector. So 0 vector, 0, c is the constant, and if you multiply it with the 0 vector, you will get back a 0 vector. And if you see that a vector multiplied by a scalar or a scalar multiplied by a vector is equal to 0 vector, then it means either c is 0 or u is 0. The vector is 0 from the top 1 and 2, using 1 and 2. And number 4, that negative of a vector, the negative of a vector is negative 1 times the vector. So how will that work? The negative 1 will get multiplied with every component of the vector. So some examples of vector spaces are given here. R2 with standard operations is a vector space. R2, standard operations. So what are the standard operations? Like if you have A1, B1 plus A2, B2. So these are two vectors from R2, and we add them, we get A1 plus A2, B1 plus B2. So this is how we define the addition of vectors. If you go back to chapter 2, there we define actually chapter 1. So addition is, we call it the component wise addition. So first component gets added to the first component, second component gets added to the second component. And the scalar multiplication will be c dot a b, or a1 b1 if you want, will be equal to ca cb. So both components get multiplied by the constant. Okay, now Rn, so this means any integer, positive integer, R raised to any positive integer with standard operations is a vector space. If we are talking about Rn, what type of vectors are going to be in there? Something like this. A vector with n components, u1, u2 up to un, and then another vector v, v1, v2 up to vn, and let these be the vectors in Rn and R be a real number. Then the standard scalar addition and scalar multiplication are going to be u plus v will be u1 plus v1, u2 plus v2, and so on, un plus vn. And c times u will be cu1, cu2 up to cun. So component wise scalar multiplication. Okay, I'll stop here and talk to you in the next video.